Prism of angle 60 degree produces angle of minimum deviation of 40 degree. What is its refractive index? Calculate the angle of incidence. So first, let's write what are the given things. First, write the given prism of angle. Angle of prism is given 60 degree. Angle of minimum deviation is given 40 degree. What is its refractive index? And calculate the angle of incidence. So use the prism formula for this. Okay. So we know that n is equal to sine of a plus d by 2 whole divided by sine a by 2. Substitute the value. Sine of a plus d by 2 sine a by 2. So here it comes 100 divided by 2, that is sine 50 degree whole divided by sine 30 degree. Okay. Calculate the sine 50 degree. Okay, look at in the Clark's table. We'll get the answer 0.766 divided by sine 30 is nothing but 1 by 2. The meaning of 1 by 2 is 0.5. So the refractive index value becomes 1.532. So this is the refractive index value. And also we should find the angle of incidence, right? And angle of incidence, observe here, in this formula sine I by sine R. When you compare with the angle of incidence part is A plus D by 2. So A plus D by 2, 60 plus 40 divided by 2. Therefore, angle of incidence is 50 degree. Yeah, this is the question. Next question. The angle of prism of refractive index 1.6 is 60 degree. Refractive index value is given, right? So it is 1.6 and angle of prism is 60 degree. A ray of light incident on one face just emerges from the other face. This is the condition. Calculate the angle of incidence at the first phase. Okay, at the first phase. So for this better we have one small diagram. This is the prism diagram. So here is a incident ray, refracted, and this is what the emergent, it should go like this, right? But according to this condition, at another phase just emerges. Okay, so that is the question. Here it is just emerging from the surface, means it is grazing over the surface. Okay, I'll show it in a red mark. See here, the refracted one is just grazing. It is coming like this. Okay, over the prism surface. Understand? So by the data, we can understand that. See, here the normal lines will meet. So when there is a just emergence, then the I2 will be 90 degree. And we have to find this I1. This is the I1, is question mark. Okay. Yeah, so I2 value is 90. So use the Snell's law. From Snell's law. N is equal to sine I1 divided by sine R1. Okay, first I want to find the I1, right? Therefore, Sine I1 is equal to n into sine R1. Therefore, I1 is equal to sine inverse of n into sine R1. So this is the equation 1. So if I want to find I1, first I should find R1 now. Okay. And this is the angle of prism A, and here is a R1 and here is a R2, right? So we know that A is equal to R1 plus R2. So let's substitute in that. A is equal to R1 plus R2. Okay. Therefore, R1 becomes A minus R2. Therefore, the value of R1 60 degree minus R2. Even I don't know what is R2 value, then call it as equation 2. If I want to find the R2, observe, the R2 and I2 comes for the second phase, right? So apply the Snell's law for second phase. Okay, apply Snell's law. For second phase, n is equal to sine I2 divided by sine R2. So we know the value of sine I2. I2 is 90 degrees, sine 90 divided by the sine R2. Sine 90 is 1, so it is 1 divided by sine R2. Therefore, sine R2 is 1 over the n, that is 1 divided by the n value it is given 1.6. So by doing 1 by 1.6, you get 0.625. Therefore, R2 becomes sine inverse of 0.625. So first find out the R2 now. So R2, I'm getting 38.68 degree. Okay. After knowing the R2 value, substitute in the equation 2. Substitute in the equation 2. Therefore, equation 2 becomes R1 is equal to 60 degree minus 38.68 degree. Yeah. So for the R1, I'm getting 21 degree, 21.32 degree. So we got the R1 value. Yes, but I want to find I1, right? So where is the I1 formula? Here, equation 1. Sine inverse of n sine R1. Okay, I will substitute here. Therefore, equation 1 becomes I1 equal to sine inverse of n into sine R1 is that n is 1.6 into sine R1 sine 21.32 degree. So I1 is equal to sine inverse of 1.6 into, yeah, do this sine 21.32 degree. How much you get? Sine of 21.32. 0.3635, 0.3635, and now multiply these two, 1.6 into 0.3635, and do the sine inverse for that. We are getting sine inverse of 0.5817 and getting 35.47 degree. Verify that. Yeah. This is the third problem. It is based on the lenses in contact. Two lenses of focal length 0.2 and 0.3 meter are kept in contact. Find the focal length of the combination. Calculate the powers of two lenses and power of the combination. Okay, so by looking at the data, we can tell that the two lenses are convex because focal lengths are positive values only. Okay, so write down what are the given. The first focal length 0.20 meter and second focal length 0.30 meter are kept in contact. Okay, focal length of the combination we have to find. Focal length of the combination and power of the individual lenses P1, P2. And power of the combination. Okay, when two lenses are in contact, so we have derived the formula, right? So focal length F1 and F2. The equivalent focal length becomes 1 by F is equal to 1 by F1 plus 1 by F2. So substitute all the values here. These two are reciprocals, right? So further we can simplify like this. We can simplify this one as a F1 plus F2 divided by F1 F2. Therefore, F becomes F1 F2 divided by F1 plus F2. Substitute the values 0.2 plus 0.3. So here we are getting 0.06 divided by 0.5. So the focal length of the combination is 0.12 meter. So this is the focal length of the combination. And next we have to find the power of the individual lenses and then the combination, right? So here we have the focal length of this combination. We can find out the focal length of the power of the combinations very easily now. Therefore, power of the combination is P is equal to by F, that is 1 divided by 0.12 meter. So we are getting the power of the combination around 8.33 diopter and focal length of power of the individual lens, right? Power of first lens. So that is P1, 1 by F1. So 1 divided by focal length of the first is 0.2. That is 5 diopter. And then power of second lens, that is P2, 1 by F2. F2 given as 0.3, 1 by 0.3, and 3.33 diopter. Yeah. Next problem. The radii of curvature of the faces of a double convex lens are 10 centimeter and 15 centimeter. Its focal length is 12 centimeter. Calculate the refractive index and power of a lens. So radii of curvature, this is just a single lens, it is double convex lens. Okay. Like this, the double convex lenses, right? So here you can trace two sphere forms here according to two spherical surfaces. The one radius of curvature come towards left R1 and another radius of curvature come towards right. You can take it as a R2. There are two radius of curvatures are given. So you can consider it as a R1 is okay 10 centimeter and R2 is minus 15 centimeter. Yeah, let's make this one R2 and this is R1. R1 and R2. Since according to sign convention towards the left, so this will be negative and this side will be positive. When the light incident in this direction, okay, opposite to the light, it should be negative. Yeah, then focal length is given 12 centimeter. Right, 12 centimeter now 0.12 meter ಅಂತ ಬರಿಬಹುದು. And find out the refractive index and power of the lens. Power we can find out very easily because focal length already given. Okay. Now by using the lens maker's formula, you already know that 1 by f is equal to, and the outside medium is air. You can just write n minus 1 by r1 minus 1 by r2. Okay. Now I want the n minus 1 here to be stereo. So I'll do one thing. I'll just substitute the values of r1 and r2. It becomes 1 divided by r1 10 centimeters there. I'll convert into meter, 0.1 meter. Okay, minus into minus become plus, and 15 centimeter I'll write it as a 0.15 meter. And this 1 by f is 1 divided by 0.12. So 1 divided by 0.12 is equal to n minus 1 into 1 divided by 0.1. I can write it as a 10 plus 1 divided by 0.15. It is 6.66. It will come. So the value is n minus 1 into 16.66. Therefore, n minus 1 will become 1 divided by 0.12 into 16.66. Let's solve this one. We are getting the answer 0.5. This is the n minus 1 value. Therefore, n becomes 1 plus 0.5. So that is equal to 1.5. This is the refractive index of the material. And we are asking to find out the power also. So P is equal to 1 over the F. Okay. It is given as 0.12. So it comes around 8.33 diopter. Please copy. Look at the problem once again. Two radius of curvature is given, and we have to find the refractive index of the material. Use the lens makers formula, find out the n value, and then find the power. Power is the reciprocal of the focal length. Yeah, the next problem. The power of a convex lens is plus 2.5 diopter in air. Find the change in power when it is completely immersed in water. Refractive index of water is given and refractive index of the lens. It is made by the glass, right? So 3 by 2, it is 1.5. Yeah. So convex lens basically when it is in air, its power is 2.5 diopter. When it is immersed in water completely, then how the power of the lens changes. Very simple problem. Let's solve this. So given is in air, right? The value of power of lens in air, that is 2.5 diopter plus 2.5 because convex lens it is. We doesn't know what is the power of lens in water, okay, and how much by what amount it changed. That is also we don't know. Change in power we have to find, and they give a refractive index of the glass 4 by 3 and refractive index of water is 1 point, that is 3 by, okay. Refractive index of water is 4 by 3. This is the value they given. So we can use the lens makers formula for this. So we know that the 1 by f, okay, is equal to n minus 1 into 1 by r1 minus 1 by r2. This is what the lens makers formula. Apply for this when it is in air. Okay, when it is in air, it's only the glass medium, right? So Ng you can take, and 1 by F is nothing but the power, so we can write it as a power in air. So we can take it as a equation 1, and second, power in water. Okay, focal length change in water, and in water, the refractive index of glass with respect to water we have to take. The lens radius of curvature never changes. Now divide these two equations. Equation 2 by 1 can get PW divided by P air is equal to refractive index of glass with respect to water minus 1 divided by refractive index of glass minus 1. Because the similar terms like 1 by R1 minus 1 by R2, it will get cancelled. Further, this can be written as, see, refractive index of glass with respect to water, we can write like this, divided by mg minus 1. Let's substitute all the values. 1.5 divided by 1.33 minus 1 whole divided by. So refractive index of glass again 1.5 minus 1. Solve for this. Solving, what do you get? Therefore, PW divided by PA. 1.5 by 1.33. 1.127 minus 1. 1.5 minus 1 is 0.5. So you can get the answer here 0.254. Okay. That is PW divided by PA. That means power of a lens when it is immersed in water will increase by 0.254 times. 0.254 into power in air. So 0.254. What is the power of the lens in air? That is 2.5 diopter. So it comes around 0.635 diopter. See, when you immerse the lens inside the water, then its power increases. Therefore, what is the change in power? Has to change as you know. Change in power. So it is 0.635 when it is immersed in water. And when it was in air, it was 2.5. Right. Okay, change in power, better you take higher minus lower value. Higher minus lower. I will take this one. Yes. So it comes 1.865 diopter. So this which of power has decreased. It's not increased, right? It is decreased. Initially it was 2.5. When it is immersed in water, the power has decreased. It came just 0.635. Yes. Let's make a correction. The power of a lens not increased, it is decreased. Initially it was 2.5 in air. The next problem, very interesting problem. A small bulb is placed at the bottom of a tank containing water to a depth of 1 meter. Find the critical angle for water-air interface. Also calculate the radius, diameter, and area of the circular bright patch of light. Refractive index of water is 1.33. Yeah. So let's imagine water tank here. Okay. Bulb is placed at this position at the bottom. Okay, bulb is glowing. So here at the surface, it's creating a circular patch. Okay. Like this. And after that, here keep tracing. This is what the critical angle they're asking, right? So this is the bulb. Here how the light is going on. So when you draw the normal for this will become the critical angle. So you can just call it as a C. Here is our critical angle, and here also the critical angle. And so this is the depth, and this is the radius of the circular patch. R. And according to alternate angle property, we can say that here also the critical angle value will be same. Now we have to find out that only what is the critical angle, and depth is given, right? It is at 1 meter depth, and refractive index of water 4 by 3, that is 1.33. And radius we have to find, diameter we have to find, and area of the patch we have to find. Use the formula. You know that sin C is equal to 1 by n. Sin C is equal to 1 divided by 1.33. Therefore, solve this, we are getting 0.7500. Then C is equal to sin inverse of that value. So critical angle will be 48 degree 36 minutes. Next, we have to find the radius. Okay, so from this figure, consider here from the figure. We can find out the two triangles here, right? Okay, this side also it is radius R only. So consider the tan C there. From the figure, tan C. C is the critical angle. It is opposite divided by the adjacent. We can write R by H. But I want to find the radius. It is H tan C. R is equal to H is 1 meter into tan. Tan of critical angle is already found 48 degree 36 minutes. Therefore, R value becomes 1 into 1.1343. Yes, that is equal to 1.1343 meter. So this is the radius. And now we can find out the diameter. Diameter is twice the radius, 2R, 2 into 1.1343, 2.2686 meter we get. And then find out the area. Area of a circle is pi r square. Pi is 3.142 into r square 1.1343 whole square. That is equal to, we are getting 4.0426 meters square. A transparent cube of side 24 centimeter contains a small air bubble. Its apparent depth when viewed through one face is 9 centimeter, and when viewed from opposite direction is 7 centimeter. What is the actual distance of the bubble from the first face? Also calculate the refractive index of the material. Okay. What is given? The material is a transparent cube. Okay. So first, let's convert the problem into picture. So then half of our problem will be solved. See, here is a cube structure. So your 24 centimeter, right? And then from the phase one, it will be the phase one, and this is the phase two. So there is an air bubble here, somewhere here. There is an air bubble. Okay. So when you watch it through the phase one, you watch from the phase one, uh, it may be appear at the distance of 9 centimeter. But when you watch, right, that is called apparent depth from the first phase. Apparent depth is 9 centimeter from the first phase. But when you watch through the other phase, okay, so from this phase, apparent depth is how much it is? 7 centimeter. But we doesn't know what is its real depth. Okay, let the real depth be x. Real depth, it will be x. That is question mark. Don't know that. Then remaining distance is 24 minus x. Got it? So this is the problem. So use the formula that refractive index is equal to real depth by apparent depth concept. We know that refractive index is equal to real depth by apparent depth. So for the first phase, for phase one, n is equal to what is the real depth for the phase one and taken as a x, and apparent depth is 9. And similarly for the phase two, observe the diagram, phase two, real depth 24 minus x, apparent depth is 7. But the refractive index of the material never changes. Okay, whatever the direction you see, 24 minus x divided by 7. Since the refractive index of the material is same, we can equate these two equations from 1 and 2. Equate them. X by 9 is equal to 24 minus x divided by 7. Therefore, 7x is equal to, multiply this 24 into 9, get 216 minus 9x. Therefore, x value becomes 216 divided by 16. So the real depth is 13.5 centimeter, right? So this is from the phase one. From the phase one, the air bubble is located at 13.5 centimeter. And again, there is a one more question that we have to find the refractive index of the material. Right. Refractive index of material is, substitute m is equal to, in any one of the equation, I am taking equation 1, x by 9, it is 13.5 divided by 9. Yeah. Solve for this, we'll get 1.5. So this is the refracting index of the material. The next question is, a convex refracting spherical surface of two radius of curvature 0.2 meter separates two media of refractive indices 4 by 3 and 3 by 2. An object is placed in the first medium, that means at the refractive index of 4 by 3. At a distance of 2 meter, object distance is given from the refracting surface. What kind of refracting surface it is? Convex. You can see a convex refracting surface. Find the position of the image formed. Okay. Yeah. Let's convert this into picture. The given convex refracting surface. So this is the convex refracting surface. So here is the principal axis. Here is the object placed. This is an object, and here it will be the pole. And object is placed in the refractive index of the medium 4 by 3. And image here it forms. So it will be the image somewhere here. We doesn't know what is the image. Okay. This is how the light falls on the surface. And where the image comes, we don't know. Okay. So let it be somewhere here, the image point. So this image distance we have to find. This object distance is given. Since according to the Cartesian sign convention, we can take it as a -2 meter. This is the question. So use for the spherical surface formula. For a spherical surface, okay, we have the formula n2 by v minus n1 by u n2 minus n1 divided by r. That formula we have to use now. Okay, before that, make ready all the data. So your refractive index of object space, that is n1 4 by 3. I can take it as 1.33. And where the image falls, refractive index of image space. Okay, so image falls in a second medium 1.5, and object distance that is u minus 2 meter. We don't know what is image distance, but the radius of curvature is given. Radius of curvature. Since it is a convex surface, we get the radius of curvature in positive 1 plus 0.2 meter. Okay, we use the formula n2 by v minus n1 by u is equal to n2 minus n1 divided by r. Substitute here 1.5 divided by v, we doesn't know that. 1.33 plus minus 2 is equal to n2 value 1.5 minus 1.33 whole divided by the radius of curvature 0.2. Let's perform this. 1.5 by b plus 0.666. Recurring. Yeah, after solving this, we get 0.8335. Solve this. we get 1.5 V is equal to minus 0.666. Zero point 169. Therefore, V becomes 1.5, 0.169. Solve this one. Get image distance around 8.9874. So approximately we can tell that it is at 9 meter. So it is in the second medium. Got it? This is the position of the image. The same way we can do for the concave spherical surface also. Okay, but for a concave spherical surface, the radius of curvature comes in negative. Got it? For a spherical surfaces, don't forget this formula. And we can apply the for this for concave as well as a convex.